Okay, so let's look at day 4 function transformations. This is a review of what we've done before. So let's go through this and you'll say, oh my gosh, I remember these. So when we're dealing with function notation and we are messing around inside the function, that is on the x coordinate, remember your x coordinate tells you when to move left or to the right. So adjusting the x coordinate will move us left or right. When we add to the x coordinate, we shift to the left. We translate to the left. And this is what it will look like within a function. When we're subtracting k, then we have a shift to the right, and it looks like this. Now notice on the third one, the k is outside the function. So that means we've done some function, we found the y-coordinate, now we're going to add to the y-coordinate, which means we're going to shift our function up. And you'll notice we perform the function, then we add. And then when we subtract the k, we are actually shifting down. And notice again, we have our function minus k. Now we have a vertical stretch when we multiply by some constant that's greater than 1. And we say it's a vertical stretch by a factor of k, or whatever the case may be. And then we have a vertical shrink by a factor of k, or whatever it may be. So notice that here we multiply outside the function. When we're taking the negative of the function, we're actually taking the negative or the opposite of the y-coordinate, which is a reflection over the x-axis. And you'll see that it looks like this. And this is probably not the best example on which to do this, but you still need to know this one. When we look at f of negative x, this is a reflection over the y-axis. So again, this goes back to Math 8, but it's still something good to see. A review is always good. And this will look like this. Okay, so they substitute a negative x inside the function. So let's look at a few examples where we have to rely on this chart. Suppose the generic function f of x is transformed such that g of x equals x minus 2. What transformation best describes the transformation of f of x to generate g of x? Okay, well, I see that I've got x minus 2, and I see that the minus 2 is inside the function, inside the parentheses. So it appears to be this one, which says we're going to shift to the right k units, which means this one is actually going to shift to the right k units. Okay, that's what this minus 2 does inside the function. Let's consider the parent function f of x equals x squared. The graph of the function, the negative of x plus 3 squared plus 5 is the same as the function f of x after what transformations? Well, here's what we need to notice. There are actually 3 transformations happening here. And in order to do this, you should follow the order of operations, okay? So the order of operations says do what's inside the grouping symbols first. So that's what we're going to do first. And notice when we add inside, that means we're going to shift left 3 units. Then what is the next operation that's happening? Well, they're taking the negative here, and they're taking the negative outside the function, which looks like this. So we're going to make a reflection over the x-axis. And then finally, we've got this plus 5 at the end. And notice that is outside of the function, so that affects our y-coordinate. So we end up shifting up 5 units. Okay, that's how it works. So we took a simple transformation, we described it based on the function they gave us. They gave us a more complex function. We had to give the series of transformations. Now the inverse happens. I'm given a series of transformations and I have to write the function. So let's see what happens here. What would be the function rule for g of x if the graph of g of x is the same as f of x after being transformed in the following ways? First, it's going to be vertically stretched by a factor of 2. So that will take 2 times f of x, because when you stretch vertically, you're multiplying. We will translate to the left 5 units. Okay, so left means that we're actually going to add the 5. And then we translate down 6 units. Okay, so now we need to put all of that together. And when we do, we find that g of x equals 2 times f of x plus 5 minus 6. Okay, so you see all the different parts there, but we know what f is. F is x squared. So we're going to write this as our final answer, x plus 5 squared minus 6. All right, now I feel better. I thought a little incomplete on the previous one. So here's our final answer. All right, now think about the function x plus 4 squared minus 7. What would be the function rule for g of x if it is translated left 2 units and down 3 units? Okay, left 2 units, remember, means that we're going to take x plus 2, my bad. And then when we go down 3 units, that's f of x minus 3. Okay, so let's keep these in mind as we go through, and I'm actually going to do these in different colors. So g of x is going to be f of x plus 2 minus 3. Okay? But we have our f function. Our f function is here. So this is what's going to happen. So this will be x plus 4 plus 2 minus 7 minus 3. Okay. So the minus 3 is the downward shift. The x plus 2 is what translates to the left. Okay. So our final answer will be x plus 6 squared minus 10. All right, then our last one. Think about what the asymptote would be for f of x equals 2 to the x. We all know that because we've discussed this in Unit 4 a good bit, our exponentials unit. So here we know that the asymptote for f of x equals 2 to the x is y equals 0. So what would be the asymptote for the function g of x equals 2 to the x minus 4? Well, what did this do? This, let's write it this way. This function says we shift down 4 units. So everything shifts down 4 units, including the asymptote. So the new asymptote here will be y equals negative 4. And again, drawing back on when we briefly discussed transformations of exponentials, it's right there. Okay, so that's what you need to know for the asymptote of an exponential function. All right, so let's look at a few problems. We'll look at a few sample problems here. So these are problems that you might see on the end of course test that I just want to go over with you. All right, the graph to the left shows the function f of x. I want to graph the negative of f of x minus 5. So here are the things that we need to know. We need to know what transformations are occurring. So this is our first transformation. Remember, when we're subtracting inside the function, that means we're going to shift to the right 5. And then I see that we're multiplying by a negative, and that will be our reflection on the x-axis. Okay? And this is my standard parabola, x squared. So I know that 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 6, 9. So let me just plot these points on here because they will help me with my transformations. So step 1 says that we're going to shift every point that we know to the right. So that's what I'm going to do. I'll start here on the left. So we're going to go 1, 2, 3, 4, 5. So that's that new point. Let's shift this one. 1, 2, 3, 4, 5. Negative 1, 1, 1, 2, 3, 4, 5. 0, 0 becomes 1, 2, 3, 4, 5. And the cool part is, remember, in a parabola, I've got an axis of symmetry, so I get these points for free. Or I could just shift over 5 units, whichever one you want to do. So that's the initial step in graphing this. And then our final step is to reflect on the x-axis. So this point, instead of being 9 units above, 1, 2, 3, 4, 5, 6, 7, 8, 9, pardon me, instead of being 9 units above the x-axis, it will be 1, 2, 3, 4, 5, 6, 7, 8, 9 units below. This point is 1, 2, 3, 4 units above, so it reflects 1, 2, 3, 4 units below. This point is 1 unit above, its reflection is 1 unit below. This is on the axis, its reflection point stays on the axis, it maps onto itself. Here are my BOGO points because I've still got the same axis of symmetry. Okay, and so this is what my final graph will look like. It could be a better graph. All right, let's look at this graph. I would like to know which equation represents this graph. Well, the first thing I would like to do is find the axes to kind of give myself a bearing. So here's my x-axis, and then there's my y-axis. So I see that it's an exponential function, and I know that a standard exponential function has an asymptote at y equals 0. But I see that this function has an asymptote of y equals 2. So if my asymptote shifted up 2 units, then it looks like the original graph shifted up 2 units, which is, remember, f of x plus 2, which is the only one here that adds 2 to the function, the output value, b. I mean, I could talk about shifting this to the right, but let's not go crazy here. All right, number 8. And let's go and throw number 9. Which function shows the function f of x equals 3 to the x being translated 5 units to the left? Well, remember, when we're translating 5 units to the left, we're doing the opposite of what we think should happen. Remember, crazy x's do the opposite of what we think? That happens here. So if we're shifting to the left, we're adding to x inside the function. Which one of these adds to the x inside the function? Well, this is the only one. Just so you know, this one goes down 5. This one will go to the right 5, and then this one shifts up 5, just in case you wondered why the others didn't work. Okay. Which function shows f of x equals 3 to the x being translated 5 units down? Well, that's outside the function, and we subtract. So which of these shows that? Oh, there it is, number 9. I mean, letter A for number 9, my bad. Okay, which statement best describes the graph of f of x plus 6? All right, we're inside the function, so we do the opposite of what we think. We're going to go to the left 6 units. So just in case you're wondering, this one adds outside. This one subtracts inside. This one subtracts outside. So again, I'm just kind of following the theme of my table on the first page to kind of follow along and make sure I'm getting my transformations. All right, so let's look at this last page. Which statement best describes how the graph of g of x equals negative 3x squared compares to the graph of f of x equals x squared? Well, there's some math, some operations happening. We're multiplying by 3, which is a vertical stretch by a factor of 3. But I also see that this negative sign means that we are reflecting on the x-axis. All right, so there are 2 transformations happening. If there are 2 transformations happening, then it can't be A, because that's just a single transformation. Now, is it only reflecting across the x-axis? No, so we've got to throw that one out. So by process of elimination, I've narrowed my choices down to 2. So which one of these describes a vertical stretch by a factor of 3 and a reflection on the x-axis? Oh, that's D. FYI, this one would have been, I guess I should say, this one would have been g of x equals negative 1/3 x squared. All right, number 12. The graph of the exponential function f of x equals 4 times 0.5 to the x plus 2 is shown. Which function has the same end behavior? All right, let me readjust this so that I'm not talking while I'm moving. All right, which one has the same behavior for positive values of x? All right, so here are the things that I'll notice. This has an asymptote of y equals 2. So I know that whatever function we have, we've shifted it up to. So I can throw out A, and I can throw out C. Okay, so I'm left with 2 functions that show a transformation of plus 2. So the plus 2 is the same in both of them. Multiplying by 0.5 is the same in both of them. The difference here is in the base. So this base is 1.1. That represents growth because my base is greater than 1. So this one should actually move like that. This one is decay because my base is less than 1. So it's going to go like that. So which one is it? Well, it's D, because this is decay. And how do I know it's decay? Well, it's decreasing from left to right, but it also kind of has a base right here. Notice here the base is less than 1. Okay, so that's another way. All right, which function's graph has a y-intercept of 1? And I will tell you right now, I refuse to graph those 4 functions. Instead, what I'm going to do is use my calculator, which I don't have on me right now. So what I'll need you to do is bear with me. Now, this is not a standard calculator, but you're just going to have to sort of, well, here we can do this. You'll have to take my word for it, okay? So graphically, the y-intercept is where we touch the y-axis. But remember, I don't want a graph. So what's the other way to find the y-intercept? Well, let's look algebraically. Algebraically, this occurs when x equals 0. So I think what I should do is find h of 0 for each of these. Okay, so take my word for it. For this function, h of 0, 5 times 1 is 5. So it's not that. Let's look at the next one. This is 5 times 0.5 to the 0 plus 0.5. Well, that's 5 times 1 is 5, and 5 plus 0.5 is 5.5. That does not equal 1. Let's look at option C. H of 0 will be 0.5 to the 0 power plus 1. Well, anything to the 0 power is 1, and 1 plus 1 is 2. It's not that one. So by process of elimination, it's this one. But what you'll want to do is grab a calculator and look at this. Okay. 2 to the 0 is 1. 0.5 times 1 is 0.5, and when you add it to 0.5, you do get 1. So we're just verifying. So D is the correct answer. So make sure that you're able to perform a two-step problem. One compares a graph with a function, and then the next one will just ask you a characteristic of a particular function. And then we look at a few milestones applications, sample questions. Part A, the graph of f of x is shown on the coordinate grid. Graph the linear function f of x minus 2. All right, so what's going to happen on this one is sometimes they'll give you a graph, and here's what I want you to notice. So you'll look right here and notice what we have to do is shift down 2 units. So you will choose with your mouse, you'll select the point button. And you'll take each of these points and you will shift them down 2 units. And you'll plot those 3 points. Once you've plotted the points and you're comfortable with them, you will then select the line button or the segment button. And when you do that, the calculator or the computer will graph these for you, okay? I'm trying to get this perfect. Well, we know that's not going to happen. But once you do that, once you've created your points, it will graph your line. And there it is. Or your segment, whatever the case may be, okay? So the first thing you're going to do is plot the points. And then from there, you will graph the line. Or in this problem, you would graph the segment. All right. Part B, a linear function is shown. They want you to graph g of x plus 3. Okay, so what you want to graph, g of x plus 3 equals 3/4 x minus 5 plus 3, which becomes 3/4 x minus 2. So how do we graph this linear function? Well, I know that the y-intercept is -2, and I know that the slope is 3/4. All right, so I'm going to do the same thing that I just did. I'm going to plot these points. On the y-axis, I'm going to plot a point at -2, and then I'm going to count up 3 to the right 4, up 3 to the right 4, and I'm also going to go down 3 to the left 4, okay? And I would plot those points when I select that command. Then I would choose the segment and I would let the computer just create this beautiful line for me. Okay, and so that's what transformations look like. So that's the end of comparing functions, but I did want to talk to you briefly about a special type of function, or actually two types of functions. Sometimes we talk about even functions, okay? Even functions are functions where when you have f of x and then you substitute negative x, you get the same function, okay? For example, x squared is even. And the reason why is because if you look at f of negative x, so we'll say because f of negative x is the negative of x squared, which is x squared, which, oh my gosh, is just like the original. They're the same. And what does the graph of an even function look like? Well, think about your plain old quadratic function. It is symmetric on the y-axis, so it folds over onto itself. So in a graph, we are symmetric on the y-axis. We're going to go into more detail, but I would be remiss if I didn't mention it in this Unit 5 packet because we are introducing it in Unit 5. All right, so an odd function is a function where when you substitute negative x, you get the negative y. Okay? So an example of that is x cubed. This is odd because when you take f of negative x, you will take the negative of x and cube it, which is negative x cubed, or negative of f of x. And you're saying, whoa, dear, you're really going a little crazy here. And it is a little crazy. So on a graph, it's, do you remember the 180-degree rotation? That's sort of what it looks like, okay? But what I want you to know is this, for both of these. When we're dealing with even functions, if I have xy, I can match that to negative xy. So I've got xy and I've got negative xy. When I'm dealing with odd functions, if xy is on the graph, then negative x, negative y is on the graph. And what does that look like? Well, that's going to look like this. If I have a point here, then I've got a point just like it on the other side. Remember doing that in 8th grade math when you had to do your 180-degree rotation? When I do a 180-degree rotation, I get the same thing, okay? So we actually call this symmetric about the origin. Man, I'm throwing a whole lot of stuff at you. I'm just going to remind you of the 180-degree rotation. Okay. So that's basically everything you need to know for this unit. That concludes this unit. But the key point for me is to make sure you understand how transformations work, how they look in a function, how they would adjust on a graph, and what happens to the key features, asymptotes, ranges, domains, and all that good stuff. And that's everything.